Hi everybody, I'm the greatest living inventor, and today we are doing my invention, Everest limestone mass driver. So I'll write it down. Everest limestone mass driver. Okay, so I will start with an apology. This lecture is 9 pages long, but it's the 4th time that I'm doing it. It's very, very long to explain thoroughly with drawings and stuff. So I will not draw anything, and I will not write anything also, because it's the 4th time. I never did a lecture for 3 times and failed. So I will just treat it like a podcast, okay? You just listen. I will read fast, and I hope I will finish on time. If it's more than 1 hour and 10 minutes, it doesn't record. Okay, so I'm just reading. This is a solution for the ocean acidification. Wikipedia, ocean acidification. All the links will be in the description, as always, description of the video. Okay, so this is a solution for the ocean acidification. This is not just about beautiful coral reefs. This is about the smallest creatures, plankton, who cannot build their shells because they don't have calcium carbonate, so they die. And then the whole food chain, including humans, starve to death. For example, our cattle, cows, eat minced fish. Okay, now I'm talking about the naive solution. It's not the solution, it's a step to the solution. Naive solution. The easy but deadly solution is to make neutralization of the acid. Okay, the ocean acidification, it's from the word acid. So the easy but deadly solution is to make neutralization of the acid with the base. Okay, the opposite of acid is base, that we prepare here on Earth. That's the deadly part. We have carbonic acid, H2CO3, in the water. That's the problem that's created from all our CO2. You can see in Wikipedia, carbonic acid. We take the base, which is lime water, calcium OH2. You can see in Wikipedia, lime water. I will put all the links in the description. Which is a diluted watery solution of slacked lime. In Wikipedia, calcium hydroxide, which in turn is made from mixing water with quicklime, calcium oxide, in Wikipedia. Okay, so our naive approach would be, let's make a lot of quicklime here on Earth because it's cheap. But this is very bad because of how it's made. They take limestone rock and heat it to above 825 degrees Celsius. And then all the CO2, carbon dioxide, comes out of the rock, which they throw into Earth's atmosphere. That's the deadly part. And what's left is quicklime. So in this naive method, we add CO2 to Earth's atmosphere, which is what caused the problem in the first place. So we are aggravating the original problem. Okay, so now the sophisticated solution. okay, which is the invention. It's based on the naive solution, but doing it differently, we are catching the CO2. We don't throw this in the atmosphere. We are throwing this in the atmosphere of planet Venus. Okay, I'm ready. Overview. Step 1, do the naive method, but catch the CO2 right when it's produced. Step 2, compress CO2 with very little energy. Step 3, shoot in a capsule to outer space with very little energy. I will explain everything. 4, send it to a loop around planet Venus, our neighbor. 5, release the CO2 into Venus's atmosphere. 6, capsule does a slingshot and comes back to Earth. 7, collect the empty capsule and repeat the process. Okay, so now I will break down and explain each step. Step 1, naive and catch CO2. Okay, this is the sophisticated solution. Naive and catch CO2. Do the naive solution, but catch the CO2. My example will be the Great Barrier Reef in Australia. The limestone will be quarried in Australia, maybe from limestone coast. Australia is the hottest continent, so we take the rocks to the desert in Western Australia, where we concentrate the sun rays with mirrors, like a crude reflecting telescope. Only instead of never looking to the sun rule, this telescope does, and the viewer is the chamber with the rock. In parentheses, it's like burning with the magnifying glass, only on a big scale. Close parentheses. Okay, so we concentrate the sun rays onto a chamber, like if you were a kid and you were with the magnifying glass concentrating the sun rays on a paper and burning the paper. So we are burning the rock with the same, not the same, but similar process on a grand scale. To get the required heat above 825 degrees Celsius in a metal chamber that is connected with tubes to rubber balloons. Once the balloons are filled, we seal them, we close them, so that the CO2 gas doesn't escape. The quicklime rocks that we cooked inside this chamber, the quicklime rocks are transferred back to the south side of Australia, where they are treated in seawater. This is done because that's a very exothermic reaction, Greek fire. Okay, it gives a lot of heat. And it gets over 150 degrees Celsius. If we do this near the reef above Australia, the oxygen will not melt in the water and the reef will die. Okay, now we transferred the slacked lime, okay, the product of this. We have CO2 in the balloons and we have slacked lime after we treat it with seawater. We have a slacked lime and we transfer the slacked lime to where it's needed, the Great Barrier Reef, and save the reef. The next steps are talking about how to get rid of the CO2 in the balloons in an environmentally friendly way for Earth. Okay, it's not friendly for planet Venus, but it's friendly for Earth. Planet Venus already have a lot of CO2, so we don't ruin anything. Nothing lives there. Okay, so step 2. compress and cool balloons. The balloons eventually need to get to planet Venus, but in order to shoot them into space, we need them to be a lot smaller. This means we need the gas CO2 inside to become dry ice, in parentheses, liquid CO2, close parentheses. So we need cold temperature and a lot of pressure and cold temperature. The balloons need to be compressed and cooled. So we do this with the technique that I described in my abyss elevator. Okay, it's an invention that I explained already, another invention of mine. So we do this with the technique that I described in my abyss elevator for cheap desalination of seawater invention, which means we use the fact that the pressure of the seawater increases greatly as you dive down to greater depth. This time we don't even need a hollow shaft like the elevator. We just need a long vertical rail that goes deep down. It can be located in the Mariana Trench, which is the deepest point of the ocean. Mariana Trench in Wikipedia. So we drag the balloons behind ships until they reach the vertical railway that we built there. The railway doesn't have to reach the bottom. It can be connected to a big floating rig. The way we drag these floating balloons to the abyss is with two cogwheels that are attached to the railway. Like you can see here, rack railway, locker rack system. Okay, rack railway. In Wikipedia. Also called rack and pinion railway, cog railway, or cogwheel railway. Another thing that we drag down is the hard capsule, the bullet, that the mass driver will shoot into space, which is made of aluminum coil. Okay, you can see in Wikipedia, mass driver, fixed mass drivers. We talked about what is mass driver in previous inventions. Here we are talking about mass driver, fixed mass drivers. Inside the coil, encapsulated is the capsule itself. Okay, we have a coil. We drag the balloons and we also drag a coil. Aluminum coil. I'm sorry I'm not explaining anything. You can read this here, and also this is how I ran out of time, 3 times. Inside the coil, encapsulated, is the capsule itself, the bullet, like a thin shell that protects the rubber balloons. So anyway, we are sinking both a few balloons and this whole capsule into the depth of the abyss. And down there, a robot is releasing the solid dry ice into the capsule and shuts close the capsule. Then we bring back to the water surface the empty torn balloons for recycling. And also, of course, the capsule, which is now filled with compressed CO2 and ready to be launched. Okay, step 3. How do we shoot the capsule into outer space? How do we shoot the capsule to space? Our big advantage is that the CO2 capsule is not like a spaceship with people. So we can apply big accelerations without killing the passengers, because there are no passengers. Okay, you can read this in Wikipedia, mass driver, hashtag on Earth. Wikipedia says someone calculated that for such cargo we can build a mass driver that can have enough escape velocity to escape the whole solar system with the cargo of nuclear waste. So we only need to escape Earth and reach Venus. Okay, so, but we will talk now only about getting to space, escaping from Earth. Afterwards, we will talk about how to get from Earth to Venus. Okay. Okay, so what we do now is build the biggest mass driver, electromagnetic catapult, ever inside Mount Everest. Okay, Wikipedia, mass driver. The idea is not as strange as it might sound at first, because the Chinese already want to dig a tunnel through the Everest mountain to Nepal. So it's technically possible. In 2019, there was an article in the Nepali Times by Ramesh Bhushal that said, I'm giving you all the links in the description, which way will the Tibet-Nepal railway go? Feasibility report suggests drilling a train tunnel under the Himalaya, not along the river. You can see the short interview with the engineer from 2019 here in YouTube. Tibet-Nepal Railway, an engineer's perspective, NT brief. In the video he says that it is possible to do, but it will cost a lot. Under normal circumstances, it would cost 7 to 8 million US dollars per kilometer. But for us, it would be 5 times that amount. Okay, so let's multiply by 5. We get 35 to 40 million dollars. The height of Everest is about 9 kilometers. So if we multiply by the cost per kilometer, it would be 315 to 360 million dollars. If this sounds like a lot of money, think of the military budget of the United States. Okay, Wikipedia, military budget of the United States. The fiscal year 2023 presidential budget request of 773 billion, okay, with a B, billion, 1,000 millions, 773 billion dollars. By the way, this is about 3 times more than the next country, which is China. With this much money, the USA alone can build this tunnel more than 2,000 times. Will it not be better if instead of killing each other, we will invest a little bit to saving everybody's lives? Okay, so now we are we finished with the money. We are talking about South Base Camp is in Nepal. Okay, I'm talking now about the altitude. Okay, so South Base Camp is in Nepal at an altitude of 5,364 meters, 5.5 kilometers. Okay, you can see in Wikipedia, Everest Base Camps. This is like a small village and can be our base of operations for the whole project. Okay, so in another article in the Nepali Times, this time from 2021, we see that the project stops basically because it will not earn enough money for the Chinese. But here, the international community will finance this, okay, because it's killing all the world. So I'm just quoting the other problems, not money problems. So quote, Chinese engineers found the gradient, okay, the slope, from the Tibetan plateau to the low valleys in Nepal to be too great. And there was also the need to avoid building a railway inside Nepal's protected areas in Langtang, Rolwaling and Mount Everest regions. End quote. Again, this is irrelevant for us in this project. It's too steep for a train, but we are building something completely different, in which the whole point is to reach vertical slope. And about the nature or religion protection of the mountain, we need to compensate the Nepali people, but we have to save the earth. This is crucial to the entire humanity. Okay. At the top of the mountain, where it will be hardest to drill, because this is called the death zone, okay, you can see in Wikipedia, death zone, which is about 8 kilometers altitude. Here we can do the opposite, and instead of drilling from below, we can use robots to direct acid to melt the stone from above downwards. It will be like a well, okay, a water well, but without the water, that digs itself. As long as we pump a fresh stream of acid. These acids are very dangerous. See here in the safety section about the strongest acid, fluoroantimonic acid. I don't have room to write, I will erase some of this. Fluoroantimonic acid. Okay, this is the strongest acid. Fluoroantimonic acid is a mixture of hydrogen fluoride and antimony pentafluoride containing various cations and anions, the simplest being H2F plus and Sb, this is antimony, fluor -6. This substance is a super acid that can be in excess of quadrillion times stronger than 100% pure sulfuric acid, depending on the proportions of its ingredients. Extreme care must be taken when handling fluoroantimonic acid. It is exceptionally corrosive, but can be stored in containers lined, coated with PTFE, Teflon. Okay, so PTFE. Teflon. Okay, and Teflon is a trademark of DuPont. So when I'm saying Teflon, it can be any PTFE. But the public knows this as Teflon. You have Teflon in your kitchen, in the pans and the pots, and so on. Okay, so robots carry Teflon coated tanks of this dangerous material in the same route that humans climbed the Everest, except for the robots it's easier because they are electric and don't need oxygen. Then the robots scrape clean of ice the peak of the mountain. After that, the robots deploy a tent made of stretchable, flexible fabric that contains Teflon, PTFE. We had such fabric in the 1960s, here in Wikipedia, in polytetrafluoric ethylene, PTFE, polytetrafluoroethylene. You can write in Google PTFE. You can see an advertisement from Life magazine of Zeppel. Okay, this is another trademark of DuPont, Zeppel, which is basically PTFE fabric. Okay, you can see an advertisement from Life magazine of Zeppel, the trade name used to market Teflon as a fabric treatment by DuPont corporations. The advertisement says, even if it rains pea soup. Okay, Zeppel advertisement, I'm giving you the link. It's a picture. By the way, today the most known PTFE is Teflon, which is made by Chemours. Okay, Chemours. Which is a spin-off from DuPont. Okay, so if I'm saying trademark of DuPont, maybe today it's a trademark of Chemours. Okay, so for us it's the same. Imagine the tent. Okay, so we are making a tent of PTFE fabric tent. Tent, or I'm also calling it condom, and I will explain exactly why. Okay, you will see why I call it tent or condom. Imagine the tent like a big condom that protects against the sudden burst of sperm from inside to outside and against the vaginal liquids from outside to inside. In this case, the sperm is burst of acid and rock and heat. When the acid gets in touch with moisture, okay, it explodes. This is why we first need to suck all the air out of the tent condom before we put acid in the middle of it. Okay, remember, this tent or condom is covering our digging area. It's not digging, it's melting, but our making the hole in the top of the mountain area. The vaginal fluids, so-called, are moisture from the winds outside, water clouds. This is why the tent condom needs to be anchored to the ground at the peak. Okay, there is a tent condom, and it's grounded. Okay, it's attached to the rim of the hole that we are digging or melting. This is why the tent condom needs to be anchored to the ground at the peak around the hole that we are digging. The only thing coming in and out of the tent condom are two Teflon plated straws. Today we use PTFE for the coating on catheters. Okay, when you need to pee in the hospital, they put a catheter to your urinal tract. So this catheter is like a straw. It's coated with PTFE. So here it's the same. We have a straw, so-called, made of, coated in PTFE. So it's similar. Okay, today we use PTFE for the coating of catheters, so the bacteria cannot stick to them, so it's similar. So remember, two straws. Two straws. Going in and out of the tent condom. One straw will drip in fresh new acid, and another straw will suck out old used acid, and again store it in a Teflon coated tank that is taken down in the same way that it was carried up. When the depth of the hole, okay, we dig and we dig and we dig, now it's far away for the straw to reach and suck the used acid. So when the depth of the hole doesn't allow the sucking straw to separate anymore, to operate anymore, we need to suck out the dangerous fumes, again into tanks, and then redeploy the tent condom on a lower level. Okay, we have the condom, we dig, 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 we get the condom down, we dig, 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 we put the condom even lower, we dig, 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 and so on. The sides of the hole will look like a barrel of a gun, okay, like a spiral, with spiral niche that the robots will carve for themselves, which will function like a spiral stairs. Okay, you can see in Wikipedia stairs, hashtag spiral and helical stairs. For example, see this picture in the Bramante staircase in the Vatican museums. Picture thanks to Andreas Thiele. Okay, Andreas. From Wikipedia. Okay, you have a picture of Vatican Museum staircase. It's also a staircase, spiral staircase that's going down. Let's see what time it is. 34 minutes. Okay. After the tunnel from above and the tunnel from below are united, starts the expensive part, where we need to put powerful electromagnets that are supercooled continuously, okay, inside the tunnel. The environment is cold, okay, the Everest is cold, but we need it colder. But we need the metal to be superconducting, like the magnets in an MRI machine at the hospital. Basically, it will be like building a particle accelerator, only a lot cheaper, because the particle accelerator, okay, it's not a particle accelerator, but it's like a particle accelerator. okay, like CERN. Basically, it will be like building a particle accelerator, only a lot cheaper, because the particle accelerator fine-tunes very carefully something very small, a few atoms in the micro scale or even nanoscale. And here we give a lot of linear force. Okay, we have a linear motor. Okay, the energy for the capacitors that feed the linear motors, electromagnets, okay, we have capacitors, and they give electricity all at once to the linear motors, which are electromagnets. So the energy for this needs to come through wires, okay, electrical wires. We can help China build a nuclear power station in Kathmandu Valley. Okay, you can see in Wikipedia, Kathmandu Valley. Okay, so we help China financially build a nuclear power station in Kathmandu Valley, the largest city in the Himalayan hill region. So the benefit of the people there is that they also can get electricity from this station, sponsored by the international community. Okay, from the 6 most productive nuclear power plants, half of them are Chinese. Okay, you can see this in Wikipedia. List of nuclear power stations, hashtag in service. China benefits from this project that China operates the gate to space for all future projects of any country. So next to the power plant, okay, so we build so here we build nuclear power plant. So next to the power plant there will be a transformation station. Transformation station, you can see in Wikipedia, transformer. This is to bring the electricity from the power plant so it can go through the wires to the Everest base camp, from Kathmandu to the Everest base camp. And there will be another transformation station where the Everest base camp is today. Okay, so this is like 1.5 kilometers high. This is 5.5 kilometers high, and the top is like 9 kilometers high. Okay, South Base Camp in Nepal at an altitude of 5,364 meters. Okay. I tried to understand how much money it costs to build a nuclear power station from Wikipedia. The most relevant line is this. Wikipedia, Economics of Nuclear Power Plants. I copied it. I will talk about this in a second. So if we look at the Chinese Tianwan, okay, I'm giving an example, and I will explain through an example of the biggest power station. We don't need the biggest power plant here. I'm talking now about another station, a station that is already working. Today it will be soon, it will be, according to Wikipedia, the biggest nuclear power plant, and it's in China. Okay, not far from Shanghai. So we are talking now about Tianwan. Tianwan. Okay, this is easy for me to explain through an example. But we don't need something this big. We can do it something a lot smaller. I'm doing the calculations now with you. Okay, so if we look at the Chinese Tianwan, Wikipedia, Tianwan nuclear power plant, which Wikipedia says that Tianwan will be the world's largest nuclear power plant with a total generating capacity of about 8,100 megawatts electricity. And under details it says both units of this use VVER, never mind what it is, it's something with water, pressurized water reactor, PWR, technology supplied from Russia. Together they cost approximately $3.3 billion. This is the most pricey part, the most expensive part of the power plant, but we can estimate the whole power plant will be a few billions, let's say 10 billion US dollars. Okay, so let's say about $1 billion, 10. Okay, about. Compared to how much China spends on weapons, this is very small. And it allows China to lead the whole world in space and take a commission each time someone wants to launch something into orbit. In 2022, the official military budget was announced to be $230 billion. Okay, so this is 10 billion, but China military budget is 230 billion. Okay, the second largest in the world behind the US. Wikipedia military budget of China. Okay, so we talked about water, which brings us to another problem, which is the distance from the sea. But let's finish with how much electricity we need first. The reason I'm comparing the nuclear power plant to CERN, or our project to CERN, to the particle accelerator. Remember CERN, like CERN. Okay. The reason I'm comparing to CERN particle accelerator is that they also have strong electromagnets buried in the ground between France and Switzerland. They accelerate something smaller, which is cheaper, but to a higher speed and with higher accuracy, which is more expensive. So it evens out. Okay, so I'm now taking from CERN home home.cern website in the section Powering CERN. At peak consumption, usually from May to mid-December, CERN uses about 200 megawatts of power, which is about a third of the amount of energy used to feed the nearby city of Geneva in Switzerland. So I found an article about Tian-1 nuclear power plant. The article is by Swedish company Alfa Laval and was written by Pan Haixia Gong. Okay, so I will put this in the description. Okay, it's the article is by Alfa Laval. It's a Swedish company, and the writer is Pan Haixia Gong. Okay, a nuclear milestone in China. The plant provides power mainly to the country's most developed area, southern Jiangsu, close to Shanghai. So if we look at the Jiangsu province in Wikipedia, it has population of about 84 million people. Probably the closer you get to Shanghai, the more people there are. But let's say half lives in the southern Jiangsu, which means 42 million people, but it's probably more. But let's say 42 million people. Geneva has a population of about 200,000 people. Okay, Wikipedia. So a third of Geneva is about 67,000 people. This is the electricity that is needed for CERN, 67,000 homes. And this is the electricity by Tian-1, 42 million homes. Okay, so to summarize, the Chinese power station we talked about has enough electricity for more than 600 CERN-like projects. And we talked about it, that our project is like CERN. Okay, so now for a not so easy problem, which is the distance from the sea. Every nuclear power plant is always close to the sea to get the cold water that cools the reactor. Like the Rupor nuclear power plant is cooled by a river. Rupor Rupor nuclear power plant. This is in Bangladesh. It's not our power plant, but it will be in Bangladesh. We can do this. Okay, so this is cooled not by the sea. The Rupor nuclear power plant is cooled by a river. The Rupor nuclear power plant will be a 2.4 gigawatts electricity nuclear power plant in Bangladesh, which is not far. Okay, you can see in Wikipedia. We can do the same with the river that passes through Kathmandu Valley, which is called Bagmati River. Bagmati River. In return for the non-polluting heat sink use of this holy river, the international community should help the local community clean the river and keep it clean from the current pollution. Okay, it's very polluted right now. We are not polluting it, we are just putting heat, okay, temperature. It's not radioactive. It's just heat. The distance from Kathmandu to Lukla, where the Nepalese Everest base camp is is 138 kilometers. Okay, from Kathmandu to base camp. The height is it's a steep climb, but the distance is 138 kilometers, 138. So this distance will be used to accelerate our payload at first. Okay, our payload, the bullet, is driving like this and then going up and up and up to the sky. So the first part will be from Kathmandu to here. But how do we bring our payload, the capsule filled with CO2, from the port to Kathmandu? How do we get to here? This is done by Koshi Railway. Okay, Koshi Railway. It is used to move containers and other cargo to and from Calcutta port and other places in India. Okay, this is the closest sea port. Okay, you can see in Wikipedia, Nepal Railway Company Limited, hashtag Koshi Railway. This reaches Nepal but not Kathmandu. So from there we should use trucks. Okay. What time is it? 52 minutes. Okay, this time we will finish on time. Note, important, the capsule, the bullet, contains compressed CO2. So it's like a bomb. It can explode. This means it should be driven separately from people, or at least in a safe distance at the end of the train inside an armored train car, and then inside an armored truck, like banks use to transfer money. Okay, so the full capsule bullet reached space, but now it's left with very little kinetic energy, speed, because it wasted all the energy on escaping Earth. Okay, we shoot it through Mount Everest and it barely got into space, but it doesn't have energy to go to Venus. So how do we go to Venus? How do we get it all the way to Venus and back? For this, I refer you to one of my previous inventions, which performs exactly this function, a mass driver repeater. Okay, this is something we talked about, a whole invention, so I'm not explaining it again, but this solves exactly this problem, how to take something from Earth orbit to Venus, for example, and back. After the chain of solar-powered mass drivers in this brought the package to Venus, from Earth to Venus, the package releases the CO2 in the Venus orbit, and the CO2 falls to Venus. Then we return the empty package back home, again with the mass driver repeater. This also balances the chain for the next package. Okay, I'm not explaining this idea again, you should see it, but it's another invention in another video. But the packages are balancing each other. note, only the very first package needs to be sent using another method, not this, like rockets, because there is still no returning package to balance the mass driver repeater. Okay, finally, after the empty shell is returned to Earth orbit, we land it with parachutes to the ocean, and any ship that passes sailing there can return it to the closest port by tying it with a rope behind the ship and dragging it behind it. And we give money incentive, like when you return a bottle, but of course a lot higher incentive, a lot more money. And then we recycle the shell for another night flight to Venus. Okay, so this was my invention. I'm sorry it's not with drawings. I tried and I hope it was clear, and I'll see you in my next invention. So thank you very much. Thank you.